Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1998 Nobel Prize in Chemistry, awarded jointly to Walter Kohn and John Pople, recognized the profound impact of density functional theory, or DFT, a computational quantum mechanical modeling method utilized to investigate the electronic structure, and thus the properties, of many body systems, particularly atoms, molecules, and condensed phases. Kohn's work, the focus here, revolutionized the way scientists approach the quantum mechanical description of matter, providing a practical and efficient alternative to traditional wave function-based methods, particularly for large systems. This essay will delve into the genesis of DFT, its theoretical foundations, its applications, its reception within the scientific community, and its enduring legacy. Before Kohn's groundbreaking work, the study of electronic structure relied heavily on Hartree-Fock theory and its extensions, such as configuration interaction and coupled cluster methods. These wave function-based approaches aim to solve the many-electron Schrödinger equation directly, a formidable task given the exponential scaling of computational cost with the number of electrons. In other words, each added electron drastically increased the complexity, rendering calculations for even moderately sized molecules computationally prohibitive. The fundamental limitation lay in the explicit treatment of electron correlation, the intricate interactions between electrons that govern the properties of chemical bonds and materials. Hartree-Fock theory, while providing a reasonable starting point, only accounts for electron exchange effects, neglecting the more complex dynamic correlation. Post-Hartree-Fock methods, while improving accuracy, suffered from even greater computational burdens. Therefore, a method that could capture electron correlation effects accurately and efficiently remained a significant challenge. The intellectual roots of DFT can be traced back to the Thomas Fermi model of the atom, developed in the 1920s. This model, while crude by modern standards, represented a pioneering attempt to describe the electronic structure of atoms using the electron density as the fundamental variable, rather than the many-electron wave function. The Thomas Fermi model expressed the kinetic energy of the electrons as a functional of the electron density, a crucial step towards the development of DFT. A functional, in this context, is a function of a function, meaning that the kinetic energy depends on the entire electron density distribution, not just its value at a single point. However, the Thomas Fermi model suffered from several serious limitations, including its inability to describe chemical bonding accurately. It failed to predict the existence of molecules, something of a drawback for a theory aiming to describe matter. The breakthrough that laid the foundation for model DFT came with the publication of two seminal papers by Walter Kohn and his collaborator Pierre Hohenberg in 1964, and Kohn-Sham in 1965. The Hohenberg-Kohn theorems established the theoretical bedrock of DFT. The first Hohenberg-Kohn theorem proves that the external potential, and hence the total energy, of a system is a unique functional of the ground state electron density. In simpler terms, knowledge of the ground state electron density completely determines all the properties of the system. This theorem guarantees that the electron density, a much simpler quantity than the many-electron wave function, contains all the information needed to describe the system. The second Hohenberg-Kohn theorem states that the electron density that minimizes the total energy functional is the true ground state electron density. This provides a variational principle for determining the ground state density, analogous to the variational principle used in wave function-based methods. While the Hohenberg-Kohn theorems provided a powerful theoretical framework, they offered no practical prescription for calculating the electron density. The Kohn-Sham equations, introduced in 1965, provided this crucial missing piece. The Kohn-Sham approach maps the interacting many-electron system to a fictitious system of non-interacting electrons moving in an effective potential. This effective potential includes the external potential due to the nuclei, the classical electrostatic potential due to the electron density, and the exchange correlation potential, which accounts for the many body effects of electron exchange and correlation. The Kohn-Sham equations are a set of single-particle Schrödinger-like equations that can be solved self-consistently to obtain the electron density, the key approximation in Kohn-Sham. DFT lies in the form of the exchange correlation functional. The simplest approximation to the exchange correlation functional is the local density approximation, or LDA, which approximates the exchange correlation energy at each point in space as that of a uniform electron gas with the same density. While LDA is a crude approximation, it often yields surprisingly accurate results for many systems. Generalized gradient approximations, or GGA, improve upon LDA by including the gradient of the electron density in the exchange correlation functional, accounting for the non-uniformity of the electron density in real systems. GGAs generally provide more accurate results than LDA, particularly for chemical bonding and molecular geometries. Hybrid functionals, such as B3LYP, incorporate a portion of exact exchange from Hartree-Fock theory into the exchange correlation functional, further improving accuracy. The development of increasingly accurate exchange correlation functionals remains an active area of research. Indeed, the impact of DFD on chemistry, physics, and materials science has been enormous. DFD has become the workhorse of computational materials science, enabling the prediction of the properties of materials before they are even synthesized. It is utilized for calculating the electronic structure and properties of molecules, solids, surfaces, and interfaces. Applications range from designing new catalysts to predicting the behavior of materials under extreme conditions. DFD has been instrumental in the development of new drugs, the design of new solar cells, and the understanding of complex chemical reactions. One specific example is the application of DFD to study the catalytic activity of metal nanoparticles. Researchers utilize DFD calculations to model the adsorption of reactants on the nanoparticle surface, to identify the active sites for catalysis, and to optimize the design of catalysts with improved activity and selectivity. Another example is the use of DFD in the design of new battery materials. DFD calculations can predict the voltage, capacity, and stability of battery electrodes, guiding the development of batteries with high energy density and longer lifespan. The initial reception of DFD was mixed. Some researchers, particularly those deeply invested in wave function-based methods, viewed DFD with skepticism. The approximation of the exchange correlation functional raised concerns about the accuracy and reliability of DFD calculations. There was also a lack of understanding of the theoretical foundations of DFD, with some researchers viewing it as an empirical method lacking rigorous justification. However, the accuracy and computational efficiency of DFD quickly became apparent, and the method gained widespread acceptance. The development of more accurate exchange correlation functionals and the increasing availability of computational resources further solidified the position of DFD as a leading method for electronic structure calculations. The development of DFD was influenced by a number of key figures and prior works. As previously mentioned, the Thomas Fermi model provided an earlier attempt to describe electronic structure using the electron density. The Hartree-Fock method and its extensions provided a benchmark for accuracy against which DFD methods could be compared. The work of John Slater on the X-alpha method, which approximated the exchange potential using a local potential proportional to the cube root of the electron density, also influenced the development of DFD. Kohn himself acknowledged the influence of these previous works on his own research. DFD, in turn, has had a profound influence on subsequent research. It has stimulated the development of new exchange correlation functionals, new computational algorithms, and new applications of electronic structure calculations. It has also led to a deeper understanding of the relationship between electronic structure and material properties. The development of time-dependent DFD, or TDDFD, extended the applicability of DFD to excited state properties, enabling the study of optical spectra and other time-dependent phenomena. The development of density functional perturbation theory, or DFPT, enabled the efficient calculation of vibrational frequencies and other response properties. In conclusion, density functional theory, as pioneered by Walter Kohn, represents a monumental achievement in computational quantum mechanics. By shifting the focus from the complex many-electron wave function to the simpler electron density, DFD provided a practical and efficient method for calculating the electronic structure of matter. Its impact on chemistry, physics, and materials science has been transformative, enabling the study of complex systems and the design of new materials with unprecedented accuracy. Despite initial skepticism, the method gained widespread acceptance, spurred by its effectiveness and continued refinement. The legacy of Kohn's work continues to inspire researchers today, driving the development of new theoretical methods and computational tools for understanding the fundamental properties of matter, a profound contribution to the scientific landscape.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.